Welcome back. So we've found the good estimates for x bar, y bar, standard deviation of x, standard deviation of y. We've plotted our point of averages. Now let's look at modeling an equation. If we have this scatter plot and I have an x value of 16.9 and I'd like to predict y, what would I decide to predict y as? If I draw an oval that encompasses those points as tightly as I can possibly, and I drew a line going through my point of averages might be a little higher than I drew it there, and I split that oval in half like a hot dog bun, that might be a fairly good prediction. So how would I find the equation of that line? Well, the line that splits the scatter plot oval exactly in two mirror-shaped pieces is called the SD line. SD as in standard deviation. The SD line goes through the point of averages so I know a point on the line. I know it goes through the point 11.5, 5.5, and it has a slope of the standard deviation of y over the standard deviation of x. Well, that would be 2.25 over 4.25, or 9/17. I could round that to be 0.53, but when I use my line equation formulas to find the equation of this line, I'm going to leave that value as 9/7 right up until the bitter end. If you recall your point slope formula from intermediate algebra, which was a prerequisite of this class, that says y minus the y coordinate of the point we know on our line, that would be the 5.5 guy, equals the slope, 9/17, times x minus the x coordinate of the point we know that our line goes through. If I distribute that 9/17, times 11.5 is 6.09. If I had rounded this first, it would have rounded to 6.10. And the more times I round and then use that decimal to multiply, the more my rounding is going to be off. Now I'm going to add the 5.5 to both sides. And y is, here I might change that to a decimal and round to two decimal places, 0.52, or 53, excuse me. That's my line equation. So I think my line is going to cross the y-axis at my y-intercept of 0.59 and go through my point of averages, 11.5, 5.5, that's my SD line. And this is my SD line equation. Now, if I use that line to predict an x value for, say, 17.5, Well, according to this scatter plot, I would expect my x value to lie somewhere in the oval along the slice that lines up with 17.5. But if I use my line, when x is 17.5, y would be this value. And if my x's are uniformly distributed in my oval, I would think that a little smaller, lower y value might be appropriate. I might want to pick the middle value in that slice. Notice when we slice this oval vertically, my predictions of y are a little low on the side to the left of the point of averages. I might have preferred those values. And on the right, my predictions for y might be a slightly high compared to what I might expect. So I would find that another line might be better that went something like that. That would be a regression line. We call it the line of best fit. It's the line that looks at all these points and calculates the smallest average distance from every point in the scatter plot. So let's think about finding the regression line equation. We need a new piece of information for that. We need to find the correlation coefficient, R. If you printed out the correlation coefficient table, you have 12 scatter plots you can look at. If you drew a nice smooth oval around each one of them and compared to this, which one is going to have an oval that expands out most likely to this one? I might go with R equals 0.8. Now you don't have to go with the exact numbers on the handout. You could say, oh, it's a little tighter than that. I'm going to go with 0.79 or 0.77. Or maybe it's a little narrow would be 0.81 or 0.83. Maybe it's a little fatter and you want to go down to 0.79 or 0.77. But 0.8 is good enough for me. The regression equation is y equals, the slope is the standard deviation of y over the standard deviation of x times r times x plus the y-intercept. That's the guy I don't know. So I'm going to go back to the point slope form, y minus a point on the line I know, and the regression line, like the SD line, goes through the point of averages. So it goes through y coordinate 5.5. Now, standard deviation of y over standard deviation of r times x. That's going to be 9/17 times 0.8. And then x minus the x coordinate of the point we know, the point of averages. So I have y minus, y minus 5.5. If I multiplied that together, it would round to 0.53, and I distribute that times the x. I'm not going to take 0.53 times the 11.5. I'm going to take 9/17 times 0.8 times 11.5, and that rounds to 6.09. If I use the 0.53 times 6.09, I would end up with, I'm sorry, bad teacher, I'm on the wrong, looking at my wrong notes. 9/17 times 0.8 times 11.5 is 4.87. If I had used the 0.53 times 11.5, I would have to round it to 4.88. Now we add the 5.5 to both sides, and y equals 0.53. Oh, bad teacher. Oh my goodness, this is terrible. I was using my slope, wasn't I? Because I wasn't calculating it, I was using my notes. 9/17 times 0.8 rounds to 0.42. That should be my regression line. Crossing at 0.63, going through my point of averages. Now, we usually mark a regression line with y hat. And if I wanted to predict x, or predict y, when x is 17.5, I would do y hat equals 0.42 times 17.5 plus 0.63. I'm going to do that live this time so I don't grab a stupid number. I get my y prediction to be 7.98. If I plotted that, 17.5, 7.98, that looks about like what my line might be. Should have been a little lower, but I drew that line just eyeballing it. It probably should be a little lower. The regression line is always slightly flatter than the SD line. And our SD line would be like that. And that would get you through examples A and C. Now I'll make another film to help you with example B on the regression project because it has a negative slope. And we have to do some sneaky stuff to make that happen.